Good evening. It is my pleasure to announce this year's presidential topic. Load shedding, can South Africa be saved? Load shedding is crippling South Africa. The estimated cost to the economy was as high as 899 million rands per day in 2022. Load shedding was implemented for 207 days in 2022, more than double the amount of 2021. 3,773 hours of load shedding was recorded in 2022, more than treble the hours of 2021, and the shed energy more than quadrupled in the same period. Various options have been presented to solve the problem, with small embedded generators, PV plants, wind farms, and battery energy storage being the most common suggestions. Can these technologies really solve our problems, or are there hidden pitfalls people are just not seeing? Are we just so desperate for electrical energy that we are willing to throw caution to the wind and endanger the lives of ordinary South Africans? Ladies and gentlemen, I give you the president of the institute.
Thank you, Pascal. Good evening, ladies and gentlemen. Yes, load shedding is probably on everybody's mind nearly every day of the last year, and we continue to watch apps to see when we're going to be shed again. What I'd like to talk about this evening is very briefly about the current situation, then talk about the different generation technologies that we can consider, and talk about some of the pitfalls that have not been discussed very openly, and people are so focused on just solving the problem that they forget that there are also pitfalls, and then look at possible solutions for the next few years. So for those of you that don't understand how load shedding works, it's best described as a balance between generation and load for every second of the day. If there's an imbalance, the frequency will change. And that is the holy grail of power system performance. Without stable frequency, system will fall apart. So to give you an idea how sensitive the system is, currently for about 250 megawatts of change, either in load or generation, we will have 1/10 of a hertz change in frequency. So the grid is governed within the limits of 49.8 to 50.2 hertz, which is really a very, very narrow band. If you think about a blackout, that's 5% off 50 hertz. That's how narrow the band is. So to maintain frequency, we need to load shed if there's a shortage of generation. And that's the basis why we've had all of these load shedding periods over the last 4 or 5 years. So just looking at what Pascal has said in the introduction, the number of hours of load shedding that we had last year is equal to everything that we've had before, plus some extra. And this has affected us in many ways. Let me just give some examples. Water is very much on our mind at the moment. For example, here in Gauteng, yesterday there was, and there is still today, a water shortage. One of the reasons being load shedding. It also affects sewage, and sewage plants can't operate without electricity. So sewage is dumped in our rivers. It also affects our telecommunication systems and food production. You may recall earlier this year that there was a shortage of chicken because of load shedding. So it affects our lives in a vast number of different ways. Let's also just for a moment step back out of our situation in South Africa and look at what is happening with our neighbors. And in Zimbabwe, in January, there was as much as 20 hours of load shedding per day. That means 4 hours of electricity per day. Currently, it's down to about 8 hours a day. And the reason for that is the following graph. If you look here, you will see that this blue line shows the level of Kariba Dam. And as we turned the year, you'll see that the dam was literally empty, which meant that both Zimbabwe and Zambia had to shut down their generation for a substantial period around the end of the year and the beginning of this year. Fortunately, you can see it's now picking up again. What you see here is the level of the dam in meters above sea level. So it's now about 2 meters above the minimum level again, and it's entering the rainy season. If we look at Zambia, just slightly north of us, or north of Zimbabwe, you'll see that they also experienced significant load shedding at the end of the year, last year. They were far more fortunate, though, in that they are not only reliant on Kariba Dam, but also the water coming down the Kafue River, which has been far more consistent than the Zambezi in the last year. So that meant that from February onwards, they've not had any load shedding. We then turn to Mozambique, where we import more than 1,000 megawatts of every day. You'll see that Cahora Bassa, which is the bottom end of the Zambezi River, has had a really excellent year with an energy availability factor in excess of 86%. And that is mainly because of the water that has come down the Kafue River. But this shows that in all three of these countries, we are dependent on here mainly on renewable energy. And we think that the sun will always shine. That's not necessarily the case. And if you think back a few years in the USA, there was a solar eclipse, and as the shadow moved across the North America from California to New York, they had to bring in additional generation just to cover the shadow of the moon as it moved across the USA. So I don't think that the sun always shines. Sorry, could you just move the slide on one? There's been a lot of talk as well, or at least the last 7 years, about importing electrical energy from our neighbors. And here you'll see a list of the constraints that we actually have in our interconnected system. So, for example, the transmission lines between Zimbabwe and South Africa are limited. Although we have a 400 kV link, the power transfer is really limited. And similarly, at some stages in the year, for example, we can actually get some power from Namibia, believe it or not, but that's only when Ruakana the Rokana River is in flood, which is for a short period in the fall each year. Then let's turn to our own situation and look at our system's capacity to accept new power plants. And here I'd like to show you a map from Eskom showing each dot represents a main transmission substation in the grid. And if you look at the Northern Cape, you will see this host of black dots. Those all indicate that the power system in that area cannot accept any more generation. It's constrained either by the number of transformers that are fully loaded or by the transmission lines that are fully loaded, or both. And if you look at the yellow dots in the Western and the Eastern Cape, you'll see we're already heading for the same constraint in that area. So wind farms that typically lie in this area here are very soon also going to reach the limit of what we can actually install. So although we have probably the best sunshine in the world in the Northern Cape, we cannot build more power stations there in the form of PV plants. And to alleviate this problem, building new transmission lines is going to take us about 12 years if we decide to build one now. And you might ask why that is the case. Well, the biggest delay is in getting servitudes from farmers. That's what takes the long time. Then transmission transformers are also becoming a scarce item in the world. So 500 MVA transformers now are going to take at least 2 years to build. And there's an international shortage of capacity in building these super large transformers. Then, if we just go back to this map, you'll see that the next available area is in Northwest Province. You can see how this wave of black dots is on its way to Gauteng. And if we look at Northwest Province, you'll see that in the Vryburg area, we've already been constrained with capacity. So around Klerksdorp, Potchefstroom, and Lichtenburg, there's still a lot of capacity available, and we're already seeing PV plants being built in those areas. The phenomena of having delays in building transmission lines is not something that is only unique to South Africa. It's a global problem. In the UK, for example, there's about a 10-year delay from deciding to build a power line till when you can actually commission it. And if we look at Australia, there's so much competition now for connecting to key substations that in some cases there are as many as 8 large battery projects competing for connection to the same grid point. And they are even proposing that people play a surplus, or companies play a surplus to actually win the right to connect their plant to the said substation. If we look at how renewable energy has developed or been installed in South Africa over the last number of years, you'll see that there's been a constant about 2 gigawatts that we've maintained for a number of years, and that is primarily out of generation on the Orange River and from Cabora Bassa. And then for the last few years, you've seen a very steady increase in wind and PV coming into South Africa. Now let's look at each of these possible sources in a bit more detail. Wind farms typically range from the very initial ones that were built just more than 2 megawatts up to now typical sizes are around about 100 megawatts, and there are even plants as big as 150 megawatts. And where are they built? Well, most of them are in the Western Cape, and then if you follow this dark blue line, you'll see that the mountain ranges on the border between the small and the large Karoo, and then also in the Eastern Cape. But as I've said earlier, we're soon going to run out of capacity there. And then very importantly, let's look at when the wind blows. And here I've taken an example from last year in April. Each of these light blue lines represents a day in April, given the production. And if you see we have an installed capacity of 3.1 gigawatts. And you'll see we never even reached that on any day. And that is a big problem with wind. So the actual capacity that we can get, assured capacity from wind, is around 30 to 40% of the installed capacity. And here is a cumulative graph just showing the same thing for a bit later in last year in August. And you can see here as a histogram, we can typically do assured about 1,500 megawatts. Above that becomes very unpredictable. That means that the energy availability factor doesn't even reach 40%. But turn our attention to solar farms. These range typically from 5 to 100 megawatts, and at the moment it's open season. And to just give you an example, in Northwest Province, with the last round of the renewable energy program of the government, only 3 farms were approved for round 6, although there were bids for far more. So if you look at the number of bids, you'll see that there's a total of more than 1.2 gigawatts that was offered to the government, of which they only took up not even 420 megawatts. So there's a lot of initiative in South Africa at the moment and momentum in building large PV plants. And essentially, there are 3 options that are being utilized. One is panels with a fixed angle, the second single axis tracking panels, and then the third dual axis tracking panels. And if we then look at how all of these perform, you will see that the green line represents fixed angle panels. The red is just flat panels, which are rarely used in South Africa. And then the blue is single point tracking or single axis tracking, and the black dual axis tracking. And there's not a big difference between single and dual axis tracking. So very few dual axis tracking plants are being installed simply because of their cost and the physical size that is required. If we look at their performance in the last year, and I've intentionally chose a month close to the middle of the year in terms of the sun cycle, and you will see that it peaks around midday, and still you can see this very large variation in a month in terms of the output, where we now have an installed base of about 2.2 gigawatts. Then a technology that has not really taken off in South Africa is concentrated solar power. And for those of you that don't know, there are two basic systems, one with a field full of mirrors that can tilt in two directions, and they then all focus the sun's beams on the heliostat in the middle, and then there they heat common table salt as a thermal storage medium. Here's a closer view of the heliostat, and then the second technology is a trough design where you don't have a heliostat, but the sun's rays are focused on focal point in each trough, and that makes for a far cheaper construction. And here, if we do the same that we've done with wind and PV, you will see that at the end of the day, from about 5 o'clock in the afternoon till about 10, you see the additional output that we get from the thermal storage. Now, most of the plants in South Africa at the moment are designed for about 5 hours of thermal storage. So we can utilize that in the evening peak. There is, however, a plant that is already run for 21 days non-stop, and you can achieve an energy availability factor as high as 65% for that type of plant. Then let's turn our attention to hydro. And here, one of our past presidents has been very actively involved in the Inga project, but I think it's still a pipe dream. There's too many things involved to get power from Ingula or from Inga in the DRC to South Africa. Then locally, there's about 600 megawatts of generation in the Orange River. And other than having floods like we've had in the last few months, it's primarily operated in peak hours. And if you look at the Department of Water Affairs, you'll actually see how they let out water just in those times if the dam levels are below 98%. There are still a number of possibilities for small hydro, typically run of the river. And here's an example in the Northern Cape, near Kakamas, Neusberg, which produces 10 megawatts, and last year had an energy availability factor of 82%. Then everybody knows about burning diesel in gas turbines, but I'd rather like to talk about using liquefied natural gas, and then also at a combined cycle power plant where first of all you have an aircraft derivative engine producing energy to drive a turbine and a generator, and then the waste energy, very importantly, is then put through a boiler. And if you have 3 gas turbines for every steam turbine, and you can still utilize the waste energy, you can get very high thermal efficiencies in excess of 60%. And this is typically what is done in the Middle East, where they then desalinate seawater for drinking water. And to quote Dries Wormerans, if you can have 2 gains out of a project, it's far better than only 1. And an example of that is the Drakensberg pump storage scheme that also transfers water out of the Tugela into the Vaal River system. One of the big advantages with gas turbines is how quickly we can actually put them up. And if we want to put our mind to it, international norms are typically between 24 and 30 months to put up a plant, which is really impressive. They're not completely green because we're still busy burning fossil fuels, but they use far less, or they pollute the atmosphere far less than we would by burning coal. And then very importantly, from a system perspective, they have ramp rates in the order of 10% per minute. So you'll see why that is important a bit later in my presentation. And then because they don't have coal as an energy medium, their maintenance is far lower than our coal-fired power stations. And we're heading, or we've often in the past already had a water crisis, mainly around the coast. Cape Town is a prime example of that. And if you build one of these plants close to a big metro, you can also alleviate their water shortage on a permanent basis. Right, then two more technologies that we haven't really exploited in South Africa. The first is biomass, and the other is utilizing the energy from municipal solid waste. So biomass, for example, from feedlots, in South Africa likes their meat. We have a lot of feedlots, and typically for about 20,000 head of cattle, you can produce 3 megawatts per day, 3 megawatts. So there's a lot of possibilities in that area as well. And then municipal solid waste. Each of us on average throws away 3 kilograms of waste in the dustbin every day. If you add that up, it becomes a significant amount. So in the Durban area, for example, they are now harvesting the methane from landfill. I'd rather suggest we look at solid waste incineration. And this again solves two problems. One is it contributes to our energy generation. And then secondly, we also get rid of our big waste dumps, which are a big environmental hazard. And again, they have very high energy availability factors. They run 24 hours a day, and they can run as base load. To give you an idea, there's more than 1,600 of these plants already installed worldwide. Question is, why are we not doing it? And plants typically vary in size from about 0.5 megawatt to 25 megawatts. Then let's turn our attention to energy storage, and batteries, I think, is on a lot of people's minds at the moment. And I'd like to class them in two categories. One is on an industrial scale, the typical BESS plants that produce about 100 megawatts for about 4 hours for a big plant. And then we have everybody with a set of batteries in their house or in their garage to help them through load shedding. But this, in a sense, from a system perspective, is also counterproductive, because as soon as power returns, batteries are charged as quickly as possible, referring to the residential installations. On large scale, you can control that, and that is the big advantage there. Then if we turn our attention to pump storage, if you look at Ingula, for example, more than 1,300 megawatts, and the dam can hold more than 80 hours of capacity, meaning that compared to 100 megawatts for 4 hours, they larger by a factor of 266. So shows you why pump storage is still the way to go. And then if we look at molten salt thermal storage, for example, in CSP, plants now up to 100 megawatts and storage for 12 hours. And here it's important as well, the salt doesn't age, unlike batteries. So compare that to a large battery system. They have 3 times more energy storage available. Unfortunately, South Africa hasn't invested a lot in storage in the last decade after the commissioning of Ngula. What has happened is primarily 6 CSP plants that have been put up, about 500 megawatts in total. And Eskom has had a steel port plant on the books for the last 20 years as the next site, but nothing has been developed there yet, or even plans have been announced to develop the steel port site. And if you look at both forms of thermal storage, including batteries, you'll find that they have efficiencies of somewhere between 75 and 80%. So there's not much to choose between them in that sense. Batteries respond a lot faster than pump storage and thermal to system changes, and that's probably their biggest advantage. And then battery systems can be constructed in under 2 years, whereas pump storage will take us 10 years plus. And the other advantage of hydro is that it has a very slow aging rate. In other words, the life of the plant is far longer than we'd have from a battery plant. And another key advantage is that both CSP and pump storage make use of rotating machines, and you'll see why a bit later. Turning our attention specifically to batteries, they are modular and we can even move them if need be. At the moment, I think batteries is a local solution. In other words, where there's a constraint in the system, you can utilize batteries to fully utilize the transmission network, and you get the advantage of some storage that will be available nationally. So although batteries don't add inertia, because of their very fast response, as soon as you have a loss of generation, they are able to respond very quickly to under and over frequency incidents. And that'll help counter the loss of inertia. The more PV and wind farms we put up, relatively speaking, we're losing grid inertia. And then very importantly, like with hydro or pumped hydro, you can actually schedule the recharge rate, which we can't do with household installations. And then batteries don't last forever. We need to replace them every 7 to 10 years, which makes batteries expensive. And you need to install, for example, battery storage or pump storage with PV or wind so that it is available when you want the energy. So people forget that if we look at the price just of PV, they see 60 cents or less a kilowatt hour now for large scale plants, but they forget that you still need to have the storage so that we can cover the evening and the morning peak. And you actually need to factor that in. And as soon as you do that, you'll find that technologies like thermal storage now become very attractive with CSP plants. And then batteries don't make any contribution to system fault level, another big negative of batteries, and furthermore, they also pollute the system with harmonics. So then I'd like to talk about diesel, and just like the institute here, just outside the wall, we have a diesel power generator. But before I go there, I'd like to suggest that we convert all the big gas turbines that currently run on diesel to LNG, because the operating costs are far less, and then also convert them in combined cycle to crank up their efficiency from around 40% to 60% plus. So I think that is a fairly easy, quick fix that we can do. Diesel plants typically have low efficiency in the orders of 30 to 40%. And they're very expensive to run simply because of the cost of diesel. However, they all have very fast ramp rates. So in the cases where we need to support the grid with a loss of generation, they can respond very quickly. What we haven't done yet with all of these diesel engines is to follow the lead of Australia. In Australia, the utilities have actually gone into contracts with owners of all these diesel plants. And they then hire their diesel plants from them for a period of about 10 years. And they would then maintain them, and they can then call on them whenever they need them. So instead of everybody using their diesel generator to supply 60 or 50 or 70% of the load, the utility can then run them at full load and have the benefit for the whole country. And I think that's something that we can very quickly roll out. The capital has already been spent. We simply need to just put a model like this into place. Then let's talk briefly about coal-fired plants. And if you've listened to Andre de Ruyter in the last few months, you may have picked up that he said that banks are no longer willing to provide loans for coal-fired power plants. And similarly, large insurance companies are not willing to do the same, mainly because of environmental pressures from lobby groups. So we're not going to build new thermal coal plants anytime soon. But we can fix that we have. And that typically takes 36 months to do per unit, because you've got to order spares, plan, and eventually execute it in the last 6 months. And if you think there are 80 units, there's a long road ahead in that sense. And then there's increasingly environmental pressure to decrease the emissions from all our coal-fired power stations. And some of them are already constrained simply because of that. And then we mustn't also forget the impact of coal mining on the environment. Then I'd briefly like to talk about nuclear power. For those of you who don't know, you can get units as big as 2,000 megawatts. The problem is they take forever to build. And typically now the commissioning time, or from start to commissioning, somewhere between 15 to 20 years if you look at the international average. Some of them even extend beyond that. Then South Africa, we developed the pebble bed technology, which has been closed down, but in other parts of the world, it's being pursued. It's still a relatively new technology, and I don't think utilities will look at pebble bed reactors other than for trial runs on a commercial basis very soon. And typically their size varies from about 10 to 250 megawatts. But nuclear power is a green technology and probably something that in the long run we need to pursue. But on the other hand, there's also a lot of opposition to nuclear power across the world. In South Africa, in that respect, is not an exception. So what can we do in the next 3 years? Because I think this is where our immediate challenge is. Yes, we can put up wind farms, and we can do that in less than 2 years. But as I've shown you, the wind blows when it likes, and it's not predictable. PV, on the other hand, is far more predictable, and we can build them in the same time. However, they only operate when the sun shines, and our crisis is going to move from load shedding right across the day as soon as new PV plants come online to mainly load shedding early in the morning and in the evening peak. CSP is, I think, a technology that we really need to pursue, and you need to compare that to either wind or solar plus batteries, because CSP has built-in thermal storage, and we can again build them in about 2 years. So I think we need to build far more CSP plants. Hydro, there's not much room for a big step change in hydro in South Africa at the moment. LNG, yes, we can do that, and there's the possibilities. And just think for a moment what has happened in Europe with the war in the Ukraine. Germany, for example, replaced the gas storage facilities within 200 days of them deciding that Russia is a risk. In the Netherlands, they did it in 160 days. Shows you where there's a big need and a national will, things can come together very quickly. Biomass and municipal solid waste, I think we also need to pursue. It's on a far smaller scale, but it solves a number of other problems at the same time. And again, it can be done very quickly. If I turn our attention to thermal storage, batteries and CSP again can be done very quickly, typically in a 2-year window. And I've made the suggestion that we fully utilize the resources that we have with diesel power. Those can really be available within months if we really want to. Coal, we can only use what we have. We're not going to build anymore. And that'll take us quite some time to get all these units back online. And I don't think nuclear is an option at the moment, again, because of its delay, but in 3 years. So looking at these options, what can we conclude from them? First of all, PV and wind farms are green, but the biggest problem is the energy availability factor, which is low. Wind is unpredictable, and PV only works when the sun shines, and it drops off in the afternoon very rapidly. PV is going to help us in the day with load shedding, but as soon as the sun goes down, we're going to be in trouble again. And then secondly, residential PV is not controllable from a national level. We can't control the output, so everybody that puts one up is going to use them as much as they can. And this is a problem that's going to hit us in the near future, is as the PV installation becomes bigger and bigger in South Africa, you'll see that we're going to have a big dip in the middle of the day in terms of required generation from other sources. And that will mean that the ramp rates in the early morning and the evening are going to be very high. And I'm not sure that our thermal plants will actually be able to meet that. So if we're going to use PV and wind, we need to add storage with that. And we've been very slow in taking up storage. And the government is looking at putting up a few plants, but we're not talking about serious energy storage yet. And then you must remember that PV, wind, and batteries, they all pollute our grids with harmonics. So that is becoming a far bigger problem in the foreseeable future. And the harmonics and the switching rates of our power electronics have affected many of the transformers installed in wind and PV plants, not only in South Africa, but worldwide. And PV and wind makes no contribution to fault levels or system inertia, things that we really need in places like the Northern Cape. And to date, we haven't really utilized the reactive power control that we can on PV and wind either. So again, we're falling short of a lot of our objectives in that respect. And then if you turn to residential installations, we're going to run into problems with everybody putting up PV in their backyard or on their roofs, because residential grids have not been designed for high voltage conditions, particularly in midday when the load is low. You can actually get a reversal of power flow and very high voltages. So that'll provide a lot of challenges to municipalities in that respect in the coming months. And further word of warning, in Australia, the system operator, as far back as 2017, has already declared that there's a shortage of system strength, and a year later also a shortage of inertia. And 5 years on, 6 years on, they haven't solved the problem yet. So it's going to hit us as well as a wall, and we'll have to deal with it. And that's the stage. I see no plans to prevent that from happening in South Africa. And then we also comfortably forget about the technology of the inverters, where if there's a challenge to the inverter in terms of operating conditions, the inverters will first of all protect themselves to protect their switching elements and not support the grid. Whereas if you look at synchronous machines, for example, they're designed to actually run into the red for a short period of time and help the system. So the moment we have a massive boom in PV sales, not only residentially, but on an industrial scale as well, big power plants are going up like mushrooms. So as I've said earlier, that's going to make a big difference to load shedding in the foreseeable future in daylight hours, but it's going to still catch us in the evenings and the early mornings. And that is going to make that our operation of our grid is going to become far more challenging. National control of the system operator will have to change its mind in the way that it's going to operate the grid, because things are not going to be like they used to be. And one of example is the big valley that we're going to now get because of PV in the middle of the day. So the way that we operate pump storage will also have to change. We will probably move in the foreseeable future from a 2-cycle to perhaps even a 4-cycle every day. And then I think the crisis in South Africa has not been large enough. We've only in the last few months really realized how big the problem really is. So far, we've gotten away with inverters and batteries and things like that, and we've been able to survive, but I don't think we all realize how big the problem really is. And secondly, we've not used all our resources fully that are available. Let me give you another example. Most of the PV plants have 5 to 10 to 15% reserve capacity that they have not sold on to Eskom because of contractual reasons. But the capacity is there. We simply just need to use it. And it's available immediately. So what should be done now? Well, first of all, use all the spare capacity that we have, both in, for example, PV plants and in all the diesel plants that we have around the country. And then let's repair broken units that are coal-fired power stations post-haste. That's going to take some time. And then I beg you that we invest in rotating machine technology and not only in power electronics. And as such, look at things like CSP, combined cycle gas turbines with desalination, biogas, and also at synchronous condensers. Synchronous condensers have gone out of fashion in the 1980s and 1990s. And you'll see that in the last 20 years, there's an increasing surge in the production of synchronous condensers again. And this is one of the ways that Australia, for example, is countering their weakening system strength, is by using synchronous condensers. And then in conclusion, I'd just like to show you how the pendulum swings. If we go back 100 years in South Africa, we had a lot of small power plants. Each municipality had its own small power station. And we had the largest private IPP in the world at the time, the Victoria Falls Power Company. It coexisted with Eskom from 1924 to 1948. And when Eskom bought the VFP for the staggering amount of £13.5 million in 1948, the VFP was still the largest utility. It is also a true utility in that it didn't only provide electric energy to South Africa, but it also provided compressed air to all the mines on the Witwatersrand. So they were far ahead of their time. And if you go around Gauteng and you get to a network that is operated at 44 kV, it is a VFP installation. And if you go to the far East Rand, there's a transformer there that was built in 1932. It's still running. And there's not N-1, it's just N. Says a lot, 88 to 44 kV, 54 MVA. And then we've had the National Power Company. And just look what is 100 years later. We're again putting up small power plants. We're having large private power stations, the form of IPPs, 100 megawatt plants. And we still have a national grid. So pendulum has swung completely back to where we were 100 years ago. Ladies and gentlemen, there's a list of references that you can consult if you wanted to. And thank you for your attention.
Thank you, President. Interesting topic indeed. Office bearers, you may come back up front. Madam JVP, Junior Vice President, you can join the office bearers. Okay, I wish to call on past President Engineer SAIEE AGM to propose the vote of thanks.
Thank you, Deputy President. I think I must just join my predecessors basically, and first of all, congratulate our newly elected President, Prof. Jan, as well as the newly elected Deputy Presidents that's sitting here. I think you should be sitting this side, but it's fine, I'm just joking. Our junior vice president and our senior vice president, who I guess is online as well. And then Jacob as the honorary president. And then definitely the immediate past president. I did tell him that his job only starts now. He's got to hold their hand for another year at least. So congratulations to all of you firstly. Then I'd just like to congratulate Prof. Jan on his excellent presidential address. I think, Mike, you've literally taken the words out of my mouth. It was a very pertinent topic in terms of what we currently are going through in terms of the crisis in South Africa. It was very thought-provoking as well. And I think you specifically highlighted the pitfalls as well as all the issues that we've got in terms of the power systems that are interlinked, as well as the power constraints that we have with the various technologies, including the new energy sources. So you see, I couldn't sleep, I had to take notes. And as well as the store energy, you've covered the batteries quite in detail, as well as the pump storage, the thermal storage, the diesel power, and the nuclear power. But I think towards the end, you've actually gone into detail with regard to the limitations, as well as what we should do now. So the reason that I'm also highlighting these specific highlighters of your speech is to say that I think there's a lot of research, a lot of work that has gone into it, a lot of effort that's gone into this presidential address. So I'd like you all to give him a real round of applause. So once again, just want to thank you very much, and I wish you well in your term. Thank you, Prof. Jan.